On the 23rd of July, 2012, the Sun threw 1 billion tons of plasma into the void. It crossed the orbit of Earth at more than 3,000 kilometers per second. It passed directly through the point in space where our planet had been 9 days earlier. A spacecraft called Stereo A was waiting there, a machine we had launched 6 years before to watch the Sun from a vantage point no one had occupied. The instruments on board measured the magnetic field at 80 nanotesla. They recorded the velocity. They watched the cloud pass. And when the data reached the ground, the scientists who read it understood that a storm with enough energy to collapse the electrical grids of every industrial nation on Earth had missed us by just over a week. The last time a storm of this magnitude struck the planet was 1859. It is called the Carrington event, and it arrived only 17 hours after the flare that produced it. Hello, and welcome to Sidereal. This is a series about the universe, and about the events some observed, some only narrowly avoided, that reveal what kind of universe we are living inside. Tonight, a collection of those events. Close calls, unsolved signals, things that grew where they should not have, and things that passed through us without leaving a trace. If you would like to support the channel, you can subscribe and like the video. If you want to help the algorithm understand who it is serving, leave a comment with your location and the time you are listening. That is always useful. But if you are already settling in, that is fine too. Let the video run. Here is the question this video is built around. We spend our lives on a planet that feels solid, under a sky that feels distant, in a body that feels like the boundary between ourselves and everything else. But the events we are going to sit with tonight suggest something different. That solid ground is crossing the path of forces we cannot deflect. The distant sky is full of objects we have lost control of. And the boundary of the body, the skin, the closed eye is permeable in ways that are not metaphorical. We are going to move through 12 of these stories. By the end, I think you will understand why the thing that passes through a dark room without touching anything is not a ghost. It is just physics we have not finished cataloguing. We begin with the Sunday. On the morning of the 1st of September, 1859, a 33-year-old English astronomer named Richard Carrington was working in his private observatory in the village of Redhill, south of London. He was drawing sunspots. This was his project, a meticulous, multi-year mapping of the solar surface, done by projecting the image of the sun through a telescope onto a white screen. At 11:18 in the morning, he saw something that should not have been there. 2 patches of white light appeared within a large sunspot group, brighter than the sun itself. Carrington later wrote that he ran out to call someone to witness the exhibition. When he returned, less than a minute later, the light was already fading. He had seen a solar flare. It was the first white light flare ever recorded by a human being. And Carrington did something unusual with his observation. He was careful with it. 18 hours later, when the largest magnetic storm in recorded history struck the Earth, he did not claim cause and effect. He published his findings in the monthly notices of the Royal Astronomical Society. And in that paper he wrote a sentence that has survived every solar physics textbook written since. One swallow does not make a summer. He was saying, in the language of his time, I saw something on the Sunday. Something happened on Earth 17 hours later. I am not going to tell you they are connected. I am going to leave that question open. The storm that followed is what we now call the Carrington event. Telegraph systems across Europe and North America failed. Sparks leapt from telegraph keys. In some offices, the equipment caught fire. In others, operators disconnected their batteries and found that the lines were still working, driven by current induced from the sky. Aurora borealis, normally confined to high latitudes, appeared in Cuba, in Hawaii, in Jamaica. In the Rocky Mountains, the sky was so bright that gold miners began preparing breakfast, thinking it was dawn. It was 2 in the morning. The physical mechanism behind all of this is a coronal mass ejection. The sun does not simply shine, it also sheds. Its outer atmosphere, the corona, is a plasma of charged particles held in magnetic loops. Occasionally, those loops become unstable. They snap and reconnect, and when they do, they can fling a chunk of the sun's atmosphere into interplanetary space. The mass of a typical coronal mass ejection is around 1 billion tons. It travels at anywhere from a few hundred to a few thousand kilometers per second. If it strikes the Earth, its magnetic field couples with our own magnetosphere, inducing currents in the ground, in pipelines, in power lines in any conductor long enough to serve as an antenna for the solar wind. The Carrington event was the strongest such storm in the modern era, but the Sun has been doing this for its entire 4.5 billion-year life, and it will continue. The question is not whether another Carrington-class eruption will be launched. The question is whether it will be aimed at us. On the 23rd of July, 2012, the Stereo mission had been designed for exactly this purpose. Two spacecraft, Stereo A and Stereo B, launched in 2006, placed in orbits that gave them a stereoscopic view of the Sun, one ahead of the Earth in its orbit, one behind. By 2012, Stereo A was positioned far enough from Earth that it could observe the Sun from an angle we could not, and on that day in July, it was directly in the path of a coronal mass ejection. The magnetic field reading came back at 80 nanotesla. For comparison, the Carrington event is estimated to have produced a field of similar magnitude somewhere between 80 and 100 nanotesla, based on the intensity of the aurora and the strength of the ground currents it induced. A typical strong geomagnetic storm, the kind that produces aurora visible in the northern United States, might measure 20 nanotesla. The 2012 eruption was not merely large, it was in the highest category of events our star is known to produce. Daniel Baker and his team at the University of Colorado Boulder published the analysis in the journal Space Weather in 2014. Their conclusion was direct. If the eruption had occurred approximately 9 days earlier, it would have struck the Earth. The consequences, they wrote, would have included widespread transformer failure, continental-scale blackouts, and a restoration timeline measured not in days or weeks but in years. The economic cost was estimated at over $2 trillion. A high-voltage transformer is not a simple piece of equipment to replace. These are custom-built, often weighing hundreds of tons, with lead times of a year or more under normal conditions. A geomagnetic storm induces direct current in the windings, causing them to saturate, overheat, and fail. If enough transformers fail simultaneously, the grid cannot be restarted. You cannot route power around the damage because the damage is everywhere, and you cannot manufacture replacements quickly because there are only a few factories in the world that build them, and they are not designed for surge demand. The stockpile of spare units, where it exists, is measured in dozens, not hundreds. A continental-scale failure would require thousands. The 2012 coronal mass ejection passed through empty space. It struck nothing. The only reason we know about it is that we had placed a machine in the dark at the right position, at the right time, and that machine told us what had crossed the gap. The 2012 event was not the only time this warning had been delivered, only at a smaller scale. On the 13th of March, 1989, a geomagnetic storm considerably weaker than a Carrington-class event by most estimates, less than half as strong, struck the Earth and found Hydro-Quebec's power grid in Canada. The collapse, when it came, was startling for how little time it took. Within about 90 seconds of the storm's onset, protective relays began tripping at a substation in central Quebec. The fault cascaded through the network in under 2 minutes. 21 gigawatts of generating capacity went offline, and 6 million people lost power, some of them for 9 hours, in the middle of a Canadian march. Aurora, normally a high-latitude phenomenon, was reported as far south as Texas and Cuba that night, the same signature the Carrington event had produced more than a century earlier, the same physics, simply weaker. The financial cost ran into the tens of millions of dollars, and it produced something the 2012 near miss alone might not have: an institutional memory. Hydro-Quebec spent the following years and roughly $2 billion reinforcing its system, recalibrating protective relays, adding equipment specifically designed to resist the kind of current a geomagnetic storm induces, building a real-time monitoring system to watch for the next one. Engineers at the utility have since said, in plain terms, that nothing had taught their industry to take space weather seriously the way 1989 did. It remains the clearest demonstration on record that a storm well short of Carrington magnitude is sufficient, on its own, to black out a modern grid in under 2 minutes. This is the fact that sits at the center of this video. A solar storm powerful enough to bring down modern civilization missed the Earth by 9 days. We have the measurements, we know the numbers, and the Sun will produce another. And there is a deeper history here than the instrumented record shows. Our direct measurements of solar storms only go back as far as our instruments do, a few centuries at most. less than that for anything precise. In 2012, a Japanese physicist named Fusa Miyake found a different kind of instrument entirely, tree rings. Examining the growth rings of ancient cedar trees, Miyake's team found a sudden, sharp spike in a radioactive form of carbon, dated to the year 774, of a size that did not match anything in the instrumented era at all. The same spike turned up afterward in tree rings from Germany, from Russia, from the United States, from New Zealand, a global signature, embedded in wood, of something that struck the Earth's upper atmosphere 13 centuries ago, and left no other trace anyone has found. What produced it remains genuinely contested. The leading explanation is an extreme solar particle event, a storm potentially far more powerful than anything the Sun has produced since. By some estimates, many times the scale of the Carrington event, though that scaling is itself disputed among the physicists who study it, and no one has fully reconciled the energy required with what we understand about how the Sun behaves. A short, powerful burst of gamma rays from somewhere outside the solar system has also been proposed, and not ruled out. No supernova remnant has been found nearby that would explain it that way either. 5 more events like it, smaller but following the same signature, have since been identified in tree rings reaching back nearly 9,000 years. We have a record of when these things have happened. We do not yet have a confident account of what, exactly, they are. This is not a side note, it is the honest shape of the problem. We can measure, with precision, a coronal mass ejection passing within 9 days of striking the Earth in 2012. We can reconstruct, hour by hour, a blackout in Quebec in 1989, and we can find, in the rings of a tree that was alive 1,300 years ago, evidence of something larger than either of those that we still cannot fully name. The Sun is not the only thing that has come close. Some near misses arrive as plasma, others arrive as rock. On the 10th of August, 1972, at around 2:30 in the afternoon, Mountain Time, a streak of light tore across the sky above Utah. It was the middle of the day, the sun was high, and the sky was the pale blue of a clear mountain afternoon. For close to 100 seconds, the brightest thing in that sky was not the sun. It entered the atmosphere traveling at roughly 15 kilometers per second on a shallow northward path, and within moments it was visible to people standing in their backyards, on highways, at gas stations, across 3 states. Witnesses described a fireball brighter than anything they had seen, trailing a column of smoke that did not dissipate for several minutes. In Missoula, Montana, a man watched it pass almost directly overhead, and then heard 2 sonic booms in quick succession, separated by several seconds, the sound arriving long after the light because sound is slow and light is not. The object had entered the atmosphere above Utah at an altitude of about 76 kilometers. It traveled north, over Wyoming, over Idaho, over Montana, on a ground track that eventually covered something close to 1,500 kilometers. Near the Idaho-Montana border, it reached its lowest point, approximately 58 kilometers above the ground. Then it began to climb again, and it left the atmosphere over Alberta, Canada, at an altitude of about 102 kilometers, continuing on into space. It did not fall. It skipped. The closest comparison is the one every account of this event eventually reaches for: a flat stone thrown across the surface of a pond at the right angle, touching the water and rising again rather than sinking. A meteoroid arriving at a shallow enough angle, moving fast enough, can interact with the upper atmosphere the same way, dipping into it, shedding mass and heat and light, and then continuing back out into the vacuum it came from, changed but not destroyed, never reaching the ground at all. The technical name for this kind of object is an earth-grazing fireball. It is a documented category. It is also, among documented categories, an extraordinarily rare one to catch this clearly. It was caught from 2 directions at once. On the ground, at Grand Teton National Park, a family on holiday photographed and filmed the object as it crossed the sky above Jackson Lake, the mountains behind it for scale, an image that would go on to become one of the most reproduced photographs in the history of meteor astronomy, not because it is dramatic in the way a photograph of an explosion is dramatic, but because it is dramatic in the way a photograph of something genuinely strange is dramatic. A clean, bright line of fire crossing an ordinary blue sky over an ordinary mountain range on an ordinary Thursday afternoon. From above, the object was caught by a different kind of witness entirely. A United States Air Force satellite, part of a network built to watch for the infrared signature of a missile launch, registered the object's heat at an altitude of about 73 kilometers as it descended, tracked it down to its lowest point, and tracked it as it climbed back out. The satellite had not been built to look for meteors. It had been built to look for something much narrower and much more specific, the engine plume of a rocket leaving the ground on the other side of the world. It found a rock instead, and recorded it with the same equipment, at the same wavelength, with no way to distinguish, in that first instant of detection, what kind of heat it was looking at. This is not the only time in this video that a system built to watch for one thing will register something it was never designed to interpret. It will not be the last. What the object actually was took longer to determine than where it had been. Early estimates, based on the brightness and the duration of the trail, suggested a diameter somewhere between 3 and 14 meters, the range reflecting genuine uncertainty about composition. A loosely packed, icy fragment of a comet would need to be larger to produce the same brightness as a dense, stony asteroid fragment of the same mass. In 1994, the Czech astronomer Zdeněk Sepleka reanalyzed the available photographic and satellite data and concluded that the object had lost a substantial fraction of its mass during the encounter, likely a third to a half of what it carried in before reaching the atmosphere, and that what remained afterward was probably smaller than what arrived, somewhere between 2 and 10 meters across, continuing on into an orbit around the Sun that still crossed the orbit of the Earth. Sepleka's analysis predicted that the remnant, smaller and faster than before, would pass close to Earth again in August of 1997. Astronomers watched for it. It was not seen. Whether it passed unnoticed, too small and too faint to catch, or whether the orbit had shifted in ways the original calculation could not fully capture, is not known. The object that skimmed across 3 states and 2 Canadian provinces in 1972 is, as far as anyone can determine, still out there, on a path that may or may not bring it close to this planet again, at a time no one currently knows. Here is the part of the story that does not show up in the photographs. Researchers who modeled the encounter afterward, working from the entry speed, the estimated mass, and the angle of approach, concluded that the kinetic energy involved, had the object been on a steeper trajectory and struck the ground or detonated in the lower atmosphere rather than skipping back into space, would have been comparable to a large nuclear detonation, not a city-leveling event in the way a much larger asteroid impact would be, but comparable by these estimates to the combined yield of the 2 weapons used at the end of the Second World War. The difference between the spectacle that hundreds of people filmed from a national park and a regional disaster was not the size of the object. It was the angle at which it happened to arrive. Nothing about the geometry of that approach was guided. The object did not choose a shallow angle out of mercy. It arrived on the trajectory its orbit had carried it on for who knows how long before that afternoon, intersected the Earth's atmosphere at the angle that orbit happened to produce, and left again because the angle was shallow enough to allow it to. A few degrees steeper, and the story told about this object would not include a photograph of mountains and a column of smoke. It would include a date that everyone in 3 states would still recognize on sight. The fireball of 1972 is usually filed under astronomy curiosities, a strange, beautiful, well-documented anomaly, the kind of footage that surfaces every few years online, with a caption explaining what it was. It is rarely filed under near misses, though that is what it was. It is rarely filed alongside Tunguska or Chelyabinsk, the impacts that did happen, because nothing here exploded, and nobody was hurt. But the energy was there. The mass was there. The trajectory was, for 90 seconds, aimed at the surface of a populated continent, and the only reason it is a home movie instead of a historical date is an angle of arrival measured in single digits of difference. We do not currently have a complete catalogue of every object large enough to do this that crosses Earth's orbit. We have a partial one, built slowly, mostly by accident, mostly from objects that announce themselves the way this one did, by becoming, briefly, the brightest thing in a clear afternoon sky. 41 years later, a similar object did not skip. On the 15th of February, 2013, an object roughly 20 meters across entered the atmosphere over the Russian city of Chelyabinsk at a shallow angle not unlike the one that saved 3 states in 1972, but not shallow enough. It exploded roughly 30 kilometers above the ground with an energy estimated at around 500 kilotons of TNT, about 30 times the yield of the bomb dropped on Hiroshima, shattering windows across 6 cities and injuring around 1,500 people, almost all of them from flying glass rather than the blast itself. No one had seen it coming. It had approached from the direction of the sun, the one blind spot every ground-based and space-based survey shares, since no telescope can usefully stare into the glare a few degrees off the star it is trying to avoid. The warning time, for a city of more than 1 million people, was 0. 2 objects, 4 decades apart, both large enough to do real damage, both arriving on shallow approaches that put the angle of entry, rather than the size of the rock, in control of the outcome. One skipped back into space and became a home movie. The other did not, and became a public health emergency measured in broken glass. The difference between the 2 outcomes was not better engineering or better luck. It was geometry, decided long before either object entered the atmosphere, by an orbit no one was tracking until the moment it arrived. Not everything that threatens us from above is a stranger. Some of it we built and launched ourselves. On the 10th of February, 2009, at an altitude of 789 kilometers above the Taimyr Peninsula in northern Siberia, 2 satellites collided. One was Iridium-33, an operational American communications satellite, launched in 1997. The other was Cosmos 2251, a defunct Russian military communications satellite that had been silent since 1995. They met at a closing speed of roughly 11 kilometers per second. Both were destroyed. The collision produced more than 2,300 trackable fragments, each one now in its own independent orbit, each one capable of destroying another satellite. This was not the first collision in space history, but it was the first time 2 intact satellites had struck each other, and it was the moment that a prediction made 31 years earlier ceased to be theoretical. In 1978, a NASA scientist named Donald Kessler published a paper in the Journal of Geophysical Research. The title was Collision Frequency of Artificial Satellites, the Creation of a Debris Belt. Kessler was not the first person to worry about orbital debris, but he was the first to formalize what would happen once the population of objects in low Earth orbit crossed a certain threshold. His argument was simple and, in retrospect, inexorable. Every object we launch into orbit has some probability of colliding with another object. The more objects there are, the higher the probability. At some point, the collision rate becomes the dominant source of new debris. Each collision creates fragments. Each fragment becomes a new projectile, and the process feeds itself, independent of any new launches. Kessler called this the collisional cascade. The term that stuck was Kessler syndrome. The physics is unforgiving. At orbital velocity roughly 7 to 8 kilometers per second in low Earth orbit, a 1 centimeter particle carries the kinetic energy of a hand grenade. A 10-centimeter object carries the energy of a large conventional bomb, and these objects are not moving in formation. They cross each other's paths at angles, at closing speeds that can exceed 15 kilometers per second. When 2 objects collide at those velocities, they do not simply break. They vaporize, partially, into a cloud of smaller fragments, each one still traveling fast enough to kill. What Kessler described in 1978 was a threshold. Below it, the orbital environment is manageable. We launch, we track, we avoid. Above it, the environment enters a feedback loop, and even if every spacefaring nation on Earth stopped launching tomorrow, the debris population would continue to grow for decades, perhaps centuries, as existing fragments collided with each other. The orbit would become a shell of shrapnel. We are not above the threshold yet, but the numbers continue to climb. The United States Space Surveillance Network tracks more than 35,000 objects larger than 10 centimeters. These are the objects we can see, the ones large enough to catalog and avoid. Below that, there are an estimated 1 million objects between 1 and 10 centimeters, still large enough to destroy a spacecraft, but too small to track individually. And below 1 centimeter, there are an estimated 130 million objects. Each one of these is a projectile, Each one was created by something: a launch, an explosion, a collision, a deliberate act. The largest single debris creation event in history occurred on the 11th of January, 2007. China conducted an anti-satellite test, launching a kinetic kill vehicle from a mobile ground platform against its own defunct weather satellite, Fengyun unsee, at an altitude of 865 kilometers. The satellite was destroyed. The test produced approximately 3,500 trackable fragments, more than any other single event before or since. Many of those fragments remain in orbit today. They will remain there for decades, some for more than a century, because at that altitude, atmospheric drag is negligible, and there is nothing to bring them down. The Iridium-Cosmos collision 2 years later was smaller in scale, but more unsettling in implication. It was not deliberate. It was not a test. It was two satellites, one working and one dead, that happened to cross paths at the wrong moment. The probability of that specific collision had been calculated in advance, and it was low enough that no avoidance maneuver was ordered. Low probability multiplied by a growing population of objects eventually produces a certainty. That is how cascades begin. The Iridium-Cosmos collision was an accident. 12 years later, the same kind of event happened again, deliberately. On the 15th of November, 2021, Russia launched a missile from its own territory and used it to destroy Cosmos 1408, a defunct Soviet-era satellite that had been silent in orbit since the early 1980s. The test was a demonstration of anti-satellite capability, and it worked exactly as intended. The target was destroyed, and the destruction produced more than 1,500 trackable fragments, immediately scattered across an altitude band that intersected the orbit of the International Space Station. The 7 crew members aboard the station, 4 Americans, 2 Russians, and a German, sharing the same sealed volume of air, were woken and directed to shelter inside their docked capsules as the debris field passed near the station's orbit. In case a depressurization forced an emergency departure with no time to spare, the immediate danger passed. The debris did not. Mission controllers have since had to maneuver the station out of the path of fragments from that single test more than once in the years that followed, nudging a multi-billion-dollar orbiting laboratory a few hundred meters at a time to avoid a collision with the wreckage of a satellite deliberately destroyed for the purpose of demonstrating that it could be done. This is the version of the Kessler problem that does not require an accident at all. Every fragment behaves identically whether it came from a collision nobody intended or a missile fired on purpose. The orbit does not know the difference. The only question that matters, once the debris is up there, is how long it stays. And the answer, at these altitudes, is measured in decades. Kessler's 1978 paper did not attract immediate attention. It was published in a specialist journal. The number of objects in orbit at the time was measured in the low thousands. The problem seemed far away, but Kessler kept working on it, refining the models, presenting at conferences where the audience was small. By the time the Iridium-Cosmos collision occurred, he had been warning about exactly this scenario for 3 decades. In an interview shortly after the event, he said something that has the quality of a man who has been patient longer than anyone should have to be. He said, "We are at the point where we have to do something." The European Space Agency now publishes an annual space debris environment report. The most recent edition contains a projection that even if every nation complies fully with post-mission disposal guidelines deorbiting defunct satellites, venting fuel tanks to prevent explosions, moving spent stages to graveyard orbits, the debris population in low Earth orbit will still increase. The collisions that will happen in the next 20 years are already locked in by the objects that are already up there. The feedback loop is not yet self-sustaining, but its components are in place. Orbital debris does not clear on its own. In the most congested region between 700 and 1,000 kilometers, there is no atmosphere to speak of, nothing to create drag, nothing to pull a fragment back down. Objects at those altitudes will remain there for generations. If the cascade begins in earnest, it will not be a single catastrophic day. It will be a slow degradation, decade by decade, as the usable orbits become more hazardous, as more satellites are lost to untracked fragments, as the cost of operating in low Earth orbit rises until it becomes prohibitive. The global positioning system, communications networks, weather forecasting, financial transactions, military reconnaissance, all of them depend on satellites that would be vulnerable. Not every danger we have built for ourselves stays in orbit, circling quietly until it strikes something. Some of it never left the ground at all, and came closer to causing irreversible damage than anything in orbit ever has. Not every near miss begins with a machine misreading a rock or a flare. Some begin with a machine misreading sunlight, in a room built for exactly one purpose. Where a wrong answer would not have produced a blackout or a headline, it would have produced a war. 3 weeks earlier, Soviet air defenses had shot down a civilian airliner, Korean Airlines Flight 007, after it strayed into restricted airspace near the Kamchatka Peninsula. 269 people died. The international response was furious. Inside the Soviet leadership, the response was something closer to dread, a conviction, widely held among the men running the country, that the United States was using the incident to test Soviet defenses ahead of something larger. The atmosphere, in the last weeks of September 1983, was not calm. It was the kind of atmosphere in which a system designed to give early warning of an attack might, for the first time, actually be asked to do its job. Just after midnight on the 26th of September, in a bunker called Serpukhov 15, a little more than 100 kilometers south of Moscow, a lieutenant colonel named Stanislav Petrov was on duty. He was not a typical watch officer. He was a software engineer, one of the people who had helped write and tune the algorithms running the system in front of him, and he held the post of deputy head of its combat algorithms department. He understood that system from the inside, in a way that most of the men who had stood his shift before him did not. The system was called Oko, the Russian word for eye. It consisted of satellites placed in long, looping Molniya orbits, positioned so that for hours at a time they could stare down at an oblique angle across the edge of the Earth, watching the horizon behind which the American missile field sat, looking for one specific signature: the sudden, intense burst of infrared heat produced by an intercontinental ballistic missile leaving its silo. If a launch occurred, the Soviet Union would have perhaps 25 to 30 minutes between detection and impact, enough time, in theory, for the leadership to decide whether to retaliate before their own command structure could be destroyed. Petrov's job, that night, was to be the first link in that decision. He was the one who would tell the generals whether to believe what the satellite was reporting. A little after midnight, the alarm sounded. A single word appeared on the display in front of him, in red: launch. One missile, the system reported, fired from a base in Montana. Petrov later described an interval of utter stillness, the kind that comes from a piece of information landing somewhere a mind is not yet ready to process it. Procedure required him to report it up the chain immediately. He hesitated, and within a few minutes, the system reported 4 more, 5 missiles, launched in sequence, from the same general direction. Petrov has described, in interviews given decades afterward, the specific thing that made him pause rather than report. A real American first strike, in the doctrine both sides understood and had built their own forces around, would not arrive as 5 missiles. It would arrive as hundreds, launched together, designed to overwhelm any possible response before a single retaliatory missile could leave the ground. 5 sequential launches did not match the shape of the attack the system existed to warn about. It matched the shape of something else, an error propagating through a chain of code, each false detection seeding the next. He had 2 other pieces of information, and neither of them helped him exactly, but neither of them hurt his instinct either. The optical telescopes mounted alongside the satellite's infrared sensors, intended to provide a visual cross-check of any detected launch, showed nothing. And the Soviet Union's ground-based early warning radar, the system that would detect the missiles directly once they rose high enough to clear the horizon, had not yet picked up anything, though by the geometry of the warning, it was still too early for it to have done so, even if the missiles were real. He had perhaps 15 minutes, by most accounts, before the question would answer itself one way or the other. Either the radar would confirm incoming missiles, or it would not. He did not have 15 minutes to deliberate calmly. He had 15 minutes in which the standard procedure passed the alert up the chain. Let the generals decide. Let the retaliation clock start running in parallel, just in case was the path of least personal risk, and the path he was supposed to follow regardless of what he privately believed. He picked up the phone to the duty officer and reported a system malfunction, not a launch. Not a possible launch requiring further verification while the response apparatus was readied. A malfunction. He told his superiors, in effect, that the most sophisticated early warning system the Soviet Union had ever built was wrong, on the basis of his own judgment, with no instrument in front of him to back that judgment up. The minutes that followed were the part of the story that does not photograph well and does not compress into a single image, because nothing happened. That was the entire content of the wait. The radar stayed quiet. No detonations occurred over Soviet territory, then or in the half hour that would have followed if the missiles had been real. Within roughly 25 minutes of the first alarm, it was clear, to everyone in that bunker, that the sky outside was exactly as empty as it had been at midnight. You are sitting, for a moment, in a room with no windows, 100 kilometers from a city of millions of people who have no idea this is happening, looking at a screen that is telling you, with the full institutional authority of every sensor and every line of code behind it, that the end of the world has already started, and the only thing left to decide is how to answer it. The protocol in front of you exists precisely so that you do not have to decide anything yourself, so that the decision is made by people with more rank, more information, more authority than a lieutenant colonel on a night shift. Following that protocol here would have been the easiest thing in the world. It would also, on the available evidence, have been wrong. The investigation that followed identified the cause with a precision the moment itself had not afforded. The date was close to the autumn equinox. At that time of year, the geometry connecting the sun, the high looping orbit of the Oko satellites, and a layer of high-altitude cloud sitting above the American missile fields in Montana lined up in a way that almost never occurred sunlight, reflecting off the tops of those clouds at an angle that the satellite's infrared sensors registered as indistinguishable from the heat of 5 rocket motors igniting in sequence. The system had not malfunctioned in the sense of a broken component. It had done exactly what it was built to do, with input that happened, for a few minutes on one night a year, to look exactly like the one thing it was built to recognize. The fix, once the cause was understood, was almost mundane by comparison to what it prevented. A second, geostationary satellite was added to the network specifically so that any future detection could be cross-referenced against a different vantage point before being treated as confirmed. The kind of failure that nearly started a nuclear war was, in the end, a problem of triangulation, a single point of view mistaking a reflection for a fire, with nothing else to check it against. Petrov did not report what he had done as heroism, then or for years afterward. His own account, given long after the Cold War ended, was that he had simply done his job, and that a 50-50 guess was the only kind of guess the situation had allowed him to make. He was not formally commended by his government at the time. The Soviet Union did not, in 1983, want a public record acknowledging that its early warning system had nearly triggered a nuclear exchange over a reflection in a cloud layer. The story became known publicly only years later, after the country that built the system had ceased to exist. What this incident shares with the others in this video is not the scale of the danger, though the scale here was, for a few minutes, total. It is the structure of the moment, a system built to detect one specific thing, fed an input that resembled that thing closely enough to satisfy every formal criterion, was corrected not by a more sophisticated machine, but by a single person who understood the system's blind spots well enough to doubt it when the formal criteria were, for once, not enough. The machine was not wrong about what it saw, it was wrong about what the thing it saw meant. The distance between those two kinds of wrong is where Stanislav Petrov happened to be standing that night. The story did not become public for 15 years. The incident stayed classified inside a collapsing institution until 1998, when Yuri Votintsev, the retired general who had commanded Soviet missile defense and who had been among the first people Petrov reported to that night, mentioned it in his own memoir. Until that book appeared, almost no one outside a small circle of Soviet military officers knew that a nuclear war had come within a single judgment call of starting, or that the judgment had been made correctly by a specific named individual on a specific night. Petrov was not rewarded for what he did. By his own account, he was initially told his actions had been noted favorably and then reprimanded separately for failing to properly log the incident in the unit's war diary and administrative oversight. In the middle of what may have been the most consequential 10 minutes of the entire Cold War, he received no formal commendation at the time. He retired from the military the following year, took a position as an engineer, and later left even that to care for his wife through her illness. She died in 1997, the year before the world learned what he had done. International recognition arrived slowly, and from outside his own country. An award from an American advocacy group in the 2000s, a German media prize, the Dresden Peace Prize in 2013, a documentary made about him the following year. He gave interviews, by most accounts reluctantly, and consistently declined the framing of himself as a hero. He maintained, until his death in 2017, that he had simply been the person on duty that night, doing the job in front of him, and that anyone trained the way he had been trained, sitting where he had been sitting, would have reached the same conclusion. Whether that is true is impossible to know. What is not in question is that the system around him was built to make the alternative easier, to make reporting the alarm, passing the decision upward, the path of least personal consequence, and that on one night in 1983, for reasons he himself never fully explained beyond his own training and his own doubt, that was not the path he took. The bunker at Serpukhov 15 has long since been decommissioned, and the Oko satellites that nearly started a war have been replaced by newer systems, cross-checked against more than one source, built specifically not to repeat that one failure. Not every piece of Cold War hardware aged so quietly, or so well. And then there is the question of what happens when something falls back. Not every object stays up there. Orbits decay. Some spacecraft are designed to come home, others are not. And when they come home anyway, the question is what they are carrying. In 1978, the answer came down over northern Canada. The Soviet satellite Cosmos 954 was launched from the Baikonur Cosmodrome on the 18th of September, 1977. It was not a weather satellite or a communications relay. It was a radar ocean reconnaissance satellite, designed to track the naval movements of the North Atlantic Treaty Organization by bouncing radar pulses off the surface of the sea. To power its radar system, it carried something unusual, a compact nuclear reactor, the Buk reactor, containing approximately 50 kilograms of highly enriched uranium-235. The reactor was not a secondary power source, it was the primary one. The satellite's radar demanded more electricity than solar panels of the era could provide in a spacecraft small enough to launch. The Soviet solution was to build a reactor that would operate for the mission duration and then, when the satellite reached the end of its life, separate from the main body and boost itself into a higher orbit, a graveyard orbit, where it would remain for centuries, safely above the operational altitudes of other spacecraft. That was the design. On the 24th of January, 1978, Cosmos 954 re-entered Earth's atmosphere over northern Canada. The separation mechanism had failed. The reactor did not boost. The satellite, with its nuclear core still attached, began to drag against the upper atmosphere and spiral downward. The re-entry was not a clean burn-up. The satellite broke apart. Fragments of the reactor scattered across a debris field of 124,000 square kilometers, spanning portions of the Northwest Territories, Alberta, and Saskatchewan. The largest pieces struck frozen lakes and tundra. The reactor core itself, or what remained of it, came to rest somewhere in the subarctic. North American Aerospace Defense Command had been tracking the satellite's decay for weeks. The United States and Canada knew something was coming down, and they knew what it carried. The question was where and how much would survive, and what would need to be done when it hit the ground. The answer was Operation Morning Light. It was a joint American-Canadian recovery effort, launched within hours of the re-entry. Personnel in full protective suits searched the frozen terrain on foot and by aircraft, carrying radiation detectors, looking for fragments of a nuclear reactor that should never have been there. The weather was brutal, with temperatures dropping to minus 40 degrees Celsius. The search teams flew in helicopters, scanning the snow for the telltale gamma-ray signatures of enriched uranium. They found 12 large pieces. 10 of them were radioactive. Some emitted radiation at rates up to 1.1 sieverts per hour, a dose that in a single hour of unprotected exposure would exceed the annual occupational limit for a nuclear worker. The largest fragment weighed several tons and lay embedded in the ice of a frozen lake. Recovery required heavy equipment, transported by air, and weeks of painstaking work in conditions that made every operation hazardous. The men who handled those pieces wore multiple layers of protective gear, but the radiation readings forced them to work in short rotations, retreating to warm shelters to let their dosimeters reset. The total cost of the recovery was approximately 14 million Canadian dollars. The Canadian government submitted a claim to the Soviet Union under the 1972 Space Liability Convention, a treaty that established that a launching state bears absolute liability for damage caused by its space objects on the surface of the Earth. The Soviet Union paid $3 million, half the amount claimed, and they did so, in the phrasing of the settlement, without prejudice. The phrase matters. It meant they were not admitting fault. They were paying, but they were not saying they had done anything wrong. The settlement took 3 years to reach. Canada filed its formal claim in early 1979, within weeks of the crash. The two governments did not sit down to seriously until the following year, and the agreement was not signed until the 2nd of April, 1981, in Moscow by the Canadian ambassador and a Soviet deputy minister of foreign affairs. It remains, to this date, the only time any state has ever filed and settled a claim under that convention. Every other launch, every other satellite, every other piece of debris that has ever damaged anything on the ground or in orbit has been absorbed, disputed, or ignored outside the framework the treaty was built to provide. Cosmos 954 is the only case the law was ever actually used for. The cause of the boost failure was never publicly disclosed by Soviet or Russian sources. Western analyses after the fact suggested either a malfunction in the propulsion system or a loss of attitude control that prevented the separation sequence from initiating. The reactor was supposed to push itself away from the satellite body and ignite a motor that would carry it to a higher orbit. Something in that chain failed. The satellite stayed whole until it hit the atmosphere and came apart. Cosmos 954 was not the only one of its kind. The Soviet Union had launched more than 30 of these radar ocean reconnaissance satellites by the late 1970s. Most performed their boost maneuvers correctly, and their reactors remain in graveyard orbits today, several dozen nuclear cores circling the Earth at around 950 kilometers, in the same region where the Kessler cascade would be most likely to take hold. But in 1983, a second satellite experienced the same failure mode. Cosmos 1402 re-entered over the South Atlantic. This time, the reactor burned up more completely in the atmosphere. The debris that reached the ocean was smaller and more dispersed, but the fact that it happened again suggested that the problem was not a one-off manufacturing defect. It was systemic. Something in the boost mechanism was unreliable, and the Soviet Union had known it, or should have known it, after the first failure. There is a particular quality to the Cosmos 954 story that settles into the mind as the room gets quiet. It is not the scale of the contamination, which was localized, or the cost of the cleanup, which was modest by the standards of international incidents. It is the image of those recovery teams in protective suits, walking across the frozen ground, picking up pieces of a nuclear reactor that had been orbiting over their heads a week earlier. The boundary between space and Earth is not a barrier. It is a gradient, and things cross it in both directions. The Soviet Union did not stop building these satellites after Cosmos 954. It added a safeguard. Beginning with the next generation of the program, the reactor core was designed to separate from the satellite at the end of its working life and boost itself into a much higher parking orbit, one stable enough to keep it away from the atmosphere for centuries rather than months. The safeguard failed twice more before it worked reliably. In January of 1983, a satellite called Cosmos 1402 suffered the same boost failure Cosmos 954 had. Its main body came down over the Indian Ocean with no debris recovered. Its reactor core, designed by then to separate and fall independently rather than ride the satellite down intact, came down 2 weeks later over the South Atlantic, near Ascension Island, and was reported at the time to have burned up completely, dispersing to background radiation levels. A later scientific study, sampling the stratosphere by high-altitude balloon more than a year afterward, found measurable enriched uranium at concentrations consistent with most of the reactor's fuel load still present in the upper atmosphere. evidence that the core had indeed disintegrated, rather than survived to the ground, but a reminder that disintegrating in the stratosphere and disappearing are not quite the same outcome. In 1988, the primary ejection system failed a third time on a satellite called Cosmos 1900. This time, a secondary backup system activated and did what the primary system had not. It lifted the reactor core clear into a stable orbit before re-entry could begin. It was the first time, after 3 previous attempts, that the safeguard worked exactly as intended. This is the part of the story that rarely gets told alongside the dramatic failures. The system was not abandoned after Cosmos 954. It was revised twice more in response to 2 further failures, before a redundant backup finally caught what the primary system had missed 3 times running. Nuclear reactors continued to fly in low Earth orbit for years afterward. The engineering got better. It did not get perfect. It got better at failing safely, which is a different thing, and a slower one to achieve than anyone in 1978 would have hoped. We put reactors in orbit. We put thousands of satellites there. We put rocket stages and bolts and paint flecks and the fragments of deliberate destruction, and occasionally, something comes back. But there is another kind of contamination that does not fall to Earth. It stays in orbit. It grows there. The Mir space station was the longest continuously inhabited orbital platform in history, before the International Space Station surpassed it. It was launched by the Soviet Union in 1986 and remained operational until 2015 years, of which nearly 10 were continuously crewed. Cosmonauts lived on Mir for months at a time, some for more than a year. They ate there, slept there, worked there, breathed there, and the station, over time, began to develop its own biology. By the mid-1990s, cosmonauts were reporting something that the engineers who designed Mir had not anticipated. Behind the instrument panels, on the structural surfaces, on the rubber seals of the windows, and occasionally on the food itself, colonies of mold were appearing. They were visible, they were spreading, and they did not respond to the cleaning protocols that were supposed to keep a closed environment sterile. The first signs were subtle, a darkening along the seams of the insulation, a faint, musty odor that lingered even after the air filters were changed. Cosmonauts described it as the smell of damp earth or of a forest floor after rain. They swabbed the surfaces with antifungal wipes, following the procedures in the flight manual. The mold would recede for a few days, then return, thicker than before. Some cosmonauts began to joke that they were not alone on the station. In 1998, a team from the Institute of Biomedical Problems in Moscow conducted a comprehensive microbiological survey of the Mir interior. They identified more than 90 species of bacteria and 80 species of fungi living on board. The genera included Aspergillus, Penicillium, and Cladosporium, names familiar from terrestrial mold, the kinds of organisms that grow in damp basements and on old bread. But on Mir, they were doing something that terrestrial mold does not generally do. They were corroding the spacecraft. The organisms secreted organic acids as metabolic byproducts. Those acids were eating into the titanium structure of the station. They were etching the quartz glass of optical equipment. Titanium and quartz are materials chosen for spacecraft, in part because they are biologically inert. Nothing is supposed to be able to consume them. But the mold on Mir had adapted. In the microgravity environment, its metabolic pathways had shifted. It was producing acids in concentrations that its terrestrial counterparts did not produce. And the standard biocides, the chemical agents used to sterilize surfaces, were less effective than they should have been. The lead researcher at the institute was Natalia Novikova. Her team cultured the organisms they had sampled from Mir and compared them to the same species grown on the ground. The space-grown strains showed increased virulence and increased resistance to antibiotics. They formed biofilms, thin, tough layers of microbial colonies that adhere to surfaces and protect the organisms inside from chemical attack. Once a biofilm is established, it is extremely difficult to remove. You can scrub the surface and still leave a reservoir of living cells embedded in the matrix, ready to regrow. The cosmonauts who lived with the mold photographed it, reported it to mission control, and continued their experiments. They cleaned the panels every week, using a vacuum cleaner fitted with a high-efficiency particulate filter and chemical wipes imported from the ground. The wipes were rated for use on space hardware, They were not rated for colonies that had adapted to microgravity. Within days of a thorough cleaning, the green and black patches would reappear, creeping out from the seams, spreading across the metal. One cosmonaut, Alexander Levakin, described the texture of the biofilm as slimy to the touch, even on dry surfaces. The humidity in the station was carefully controlled, but the metabolic activity of the mold produced its own microclimate, a warm, damp layer just above the surface where the organisms thrived. Behind the instrument panels, where the cosmonauts could not see, the mold grew unchecked. The engineers who designed Mir had not included access hatches for cleaning those spaces. They had not expected that anything would grow there. The smell of the station, by the late 1990s, was something that returning cosmonauts described without quite naming. It was a mustiness, an organic presence, the scent of a sealed room that had been occupied too long by living things, both human and otherwise. One cosmonaut, after a 6-month mission, said that the first thing he noticed when the hatch opened was the air heavy, thick, and carrying that unmistakable fungal odor. He said it took days to get the smell out of his clothes. The damage was not only cosmetic. In 1988, cosmonauts noticed a growth spreading across the outside of a viewport on a docked Soyuz spacecraft, a thick, living mat that had somehow established itself on the exterior of the hull and was, slowly, etching a web of fine cracks into the hardened quartz and titanium glass beneath it. The same organic acids that softened rubber seals and discolored insulation were, in this case, working on a surface engineers had assumed nothing could touch. Elsewhere on the station, the metabolic byproducts of the colonies oxidized electrical contacts behind one of the instrument panels, and at least one communications unit failed as a direct result, traced back not to a faulty component, but to a layer of fungal residue sitting where a clean connection should have been. The American astronaut Jerry Lininger, who spent nearly 5 months aboard Mir in 1997, wrote afterward about the smell filling the station and about a creeping unease that had little to do with any of the station's more publicized emergencies that year. A fire, a collision, a near-total loss of power, and everything to do with the quiet, ongoing fact that the spacecraft keeping him alive was also, demonstrably, being consumed from the inside by something that had not been part of the design. The mechanism behind this adaptation is not fully understood, but the broad outlines are clear. Microgravity alters the behavior of fluids at the cellular level. The currents that distribute nutrients and remove waste in a normal gravity environment do not function the same way. Cells experience different shear forces. The expression of certain genes changes. In some microorganisms, these changes activate stress responses that make the cells hardier, more resistant to environmental challenges, including the challenge of being poisoned by a biocide. What this meant on Mir was that the station was slowly being colonized by organisms it could not expel. The cosmonauts lived with the mold, they attempted to clean it, and watched it return. They accepted it as a feature of the environment, like microgravity itself, something to be managed, not solved. The implications reach past Mir, past the International Space Station, toward any long-duration mission in a sealed habitat. A Mars transit mission, with current propulsion technology, takes between 6 and 9 months each way. The crew spends that entire time inside a spacecraft that cannot be opened, cannot be vented to the outside, cannot be resupplied with fresh biocides beyond what it carries at launch. If a biofilm establishes itself in the water recycling system, in the air handling equipment, on the surfaces of the food storage containers, the crew cannot escape it. They cannot pull over. They cannot air the place out. They live with whatever grows. And the organisms are not passive passengers. They are evolving. The sealed environment of a spacecraft is an evolutionary pressure chamber. Anything that survives the initial sterilization protocols and makes it into orbit faces an environment that has never existed before in the history of life. Microgravity, elevated radiation, a closed ecosystem with a limited number of host species, and a constant input of human-associated microbes from the crew. The organisms that thrive in that environment are the ones that can attach to surfaces, form biofilms, resist chemical attack, and metabolize whatever substrates are available, including, it turns out, the spacecraft itself. The International Space Station has inherited this problem. A 2019 study from NASA's Jet Propulsion Laboratory documented multi-drug-resistant bacteria on International Space Station surfaces, including on handrails and inside the water recovery system. The organisms had adapted to several generations of cleaning agents. They were not, in any individual case, an immediate threat to crew health, but their presence and their trajectory of adaptation raised a question that no one has fully answered. What does a closed-loop life support system look like after 10 years of continuous habitation, after 20, after a round trip to Mars and back, with no external input and no way to sterilize the entire volume? The mold on Mir did not kill anyone. The cosmonauts who lived with it completed their missions and returned to Earth. But the fact of it, the visible, spreading, corrosive fact, remains unsettling in a way that resists the standard reassurance. We built a machine to live in. We sealed it and filled it with air and sent it into the only environment more hostile to life than the inside of a nuclear reactor. And then we watched as life, uninvited, found its way inside and began to eat the machine. There is a photograph taken on Mir in the late 1990s. It shows a control panel, one of the consoles the cosmonauts used to manage the station's systems. Around the edges of the panel, where the metal meets the insulation, there are patches of discoloration. Some of them are green, some are black. They are not large, a few centimeters across, but they are spreading from the seams outward, and they have the particular texture of something that is not merely deposited on the surface but growing through it. The photograph exists because the cosmonauts wanted mission control to see what they were seeing. They wanted the engineers on the ground to understand that the station was changing in ways the design documents had not accounted for. And the engineers understood. But there was only so much they could do. The station was in orbit. The mold was inside it. And the only people who could attempt to clean it were already living with it, breathing its spores, watching it spread behind the panels they were not supposed to open. The sealed room, it turns out, is not only a spacecraft. A sealed room is any environment we build and close and expect to remain as we left it. The mold on Mir was a slow demonstration that a closed system is never truly closed. It leaks. It admits life. And the life it admits adapts to the conditions it finds, even when those conditions were designed to be uninhabitable. But biological contamination is something we can at least see. We can photograph the colonies. We can culture the organisms. We can measure the corrosion rates and the antibiotic resistance and the gene expression changes. The mold on Mir was a visible problem, and visibility, even when the problem resists solution, is a kind of reassurance. You know what you are dealing with. You know where it is. Not every signal we have built machines to listen for arrives as something we can see, or touch, or culture in a dish, and watch regrow. Some of it arrives as the brief, total absence of anything at all, both before the moment and after it, with nothing in between but 72 seconds that nobody has ever been able to explain. Some signals come from machines we built to fool other machines. This one came from a machine built to listen for nothing in particular, in the hope of hearing something specific, and for 72 seconds in the summer of 1977, it did. The instrument was called Big Ear, a radio telescope belonging to Ohio State University, built into a field near the town of Delaware, Ohio. It was not a telescope in the shape most people picture. It had no dish that turned to track a target across the sky. It was fixed a flat reflector roughly 100 feet tall and over 300 feet long, angled to catch radio waves and direct them to a receiver, and it scanned the sky only because the Earth turned beneath it. As the planet rotated, a narrow strip of sky drifted past the telescope's fixed field of view. And whatever happened to be in that strip, for as long as it took the Earth to carry it through, was what Big Ear recorded. By the middle of the 1970s, Big Ear had been repurposed from a survey of distant radio galaxies to a different and much longer search, a project to listen for an artificial signal, a transmission from somewhere else, evidence that another civilization existed and was either broadcasting outward or simply leaking enough radio noise to be overheard. The project ran for more than 2 decades, almost entirely on volunteer labor, processing an extraordinary amount of data in an era when processing data meant printing it onto reams of paper and reading it by hand. The frequency the search focused on was not arbitrary. Just above 1420 MHz sits the natural emission line of neutral hydrogen, the wavelength at which the most common element in the universe quietly announces its presence everywhere, all the time. It is, among radio astronomers, something close to a universal constant, a frequency any technological civilization studying the cosmos would likely come to know, and therefore a frequency such a civilization might choose if it wanted a signal to be recognized as deliberate rather than dismissed as background noise. Astronomers sometimes call the quiet band of spectrum around it the water hole, a nod to the fact that hydrogen and hydroxyl together make water, and a nod, perhaps, to the idea of a quiet place where different forms of life might plausibly choose to meet. On the night of the 15th of August, 1977, the telescope's receiver registered something at that frequency, and it was not background noise. Nobody saw it happen. The observation ran unattended overnight, recording onto a continuous printout, and it was not until a few days later that a volunteer astronomer named Jerry Eman sat down to review the stack of data the machine had produced while no one was watching. Reading down a column of characters representing signal intensity, character by character, channel by channel, he reached a sequence that did not belong with the rest. 6, E, Q, U, J, 5, a code representing a signal so strong it had pushed the instrument's measurement scale almost to its limit. Eamon circled it in red ink and wrote a single word in the margin. The word gave the signal its name. The shape of the data was, in its way, as remarkable as its strength. The signal did not switch on and off abruptly, the way a burst of local interference typically does. It rose smoothly, peaked, and faded again over the full 72 seconds. And 72 seconds was not a coincidence. It was almost exactly the time it takes a fixed point in the sky to drift through Big Ear's stationary beam as the Earth turns beneath it. A signal with that precise a duration and that precise a shape was behaving exactly the way a real, distant, celestial source ought to behave as it passed through the telescope's field of view, not switching on, but arriving, and not switching off, but leaving. It came from the direction of the constellation Sagittarius, toward the center of our galaxy, from a swath of sky containing no known planet, no known star with any documented history of unusual activity, nothing on the catalogue that would explain why, on that one night, something at that frequency, that strength, briefly existed there. Big Ear had a second feature that made the signal both more interesting and more frustrating. The telescope's design used two adjacent feed horns, producing two slightly offset beams that would each sweep across the same point in the sky a few minutes apart as the Earth's rotation carried it through. A genuine fixed source should, in principle, have shown up in both beams, staggered by that interval. The wow signal appeared in one. It did not appear in the second, whether this meant the source had simply switched off in the gap between beams, or never produced anything in the second beam's slightly different patch of sky, or behaved in some way the instrument was not built to capture, is a question that has never been answered because the source was never detected a second time at all, not that night, not in the years of continued listening at Big Ear afterward, and not in any of the much larger searches, with much larger telescopes, conducted by other researchers since. That persistent silence has shaped almost everything written about the signal afterward. An event that does not repeat is exceptionally difficult to either confirm or dismiss. There is no follow-up observation to run, no spectrum to refine, no chance to point a better instrument at the same coordinates and ask the source to say it again. There is only the one printout, the one red circle, and 4 decades of people trying to explain a single 72-second event using nothing but its own internal evidence. Several natural explanations have been proposed. The most widely reported, put forward in 2016, suggested that hydrogen gas surrounding a passing comet, excited by sunlight, might have produced a transient emission at the right frequency as the comet crossed that part of the sky. The hypothesis named 2 specific comets believed to have been in roughly the right region decades after the fact. It drew immediate and detailed criticism from other researchers, who pointed out that cometary hydrogen comae are far fainter than what Big Ear recorded, that the orbital reconstructions placing the comets at that location on that date were contested, and that neither comet had even been discovered until long after 1977, making any precise claim about their position that night difficult to verify with confidence. The hypothesis has not been broadly accepted. Neither has any other proposed explanation, terrestrial interference included, fully accounted for the signal's strength, its narrow frequency, and its smooth, beam-shaped rise and fall all at once. More recent work has approached the question from a different angle entirely, without claiming to resolve the original event. Researchers re-examining archival hydrogen line data from a different radio telescope have found smaller, fainter signals with some of the same signature, associated not with comets but with sudden flares from small, active red dwarf stars exciting the thin hydrogen gas around them. Nothing in that newer work points back to the specific patch of sky Big Ear was watching in 1977, but it suggests, for the first time, a natural physical mechanism, stellar flare, not comet, not equipment fault, capable of producing a real signal in that same quiet hydrogen band, which had not been seriously considered before. The wow signal itself remains unexplained. The question of what kind of thing could explain it has, at least, gained one more candidate. Big Ear was demolished in 1998 to make way for a golf course expansion, its decades of printouts archived, its discoveries still sitting, unrepeated, in the data. Jerry Eman, who circled it, spent much of the rest of his career being asked what he thought it was, and gave, by every account, the same careful answer every time, that there was simply not enough information in a single 72-second printout to say anything more specific than what the data itself contained. A strong signal, a natural-looking shape, a frequency chosen, if chosen at all, with apparent care, and then nothing, for as long as anyone has kept listening since. The most recent attempt to find an answer came from a different direction entirely, narrowing down where, exactly, in that patch of sky, a signal might plausibly have originated. In 2022, an astronomer working independently used data from the Gaia Space Telescope to search the region covered by Big Ear's two beams for a sun-like star, the kind of star most likely, by reasoning alone, to host a planet capable of sending a signal at all. Out of many thousands of candidate stars in that patch of sky, exactly one fit every criterion: temperature, radius, and brightness, all close to the sun's own. It is catalogued, for now, only by a string of letters and numbers, sitting roughly 1,800 light-years away, toward Sagittarius. That same year, the Breakthrough Listen project pointed two large radio telescopes at that single star, simultaneously. For the first time, anyone had ever conducted a search aimed at this specific point in space, rather than the broad region around it. They searched for the kind of narrow, drifting signal a deliberate transmission would produce. They found nothing. A null result narrows the search. It does not close it. The star is still there. The frequency is still the one hydrogen quietly announces everywhere in the universe, all the time. And the 72 seconds recorded in 1977 remain exactly what they have always been. A single, unrepeated entry in a printout, circled in red, waiting for either a second detection or a better explanation, whichever arrives first. The next thing we are going to sit with is different. It is not visible. It left no photograph. It was a signal, a pattern of light recorded by a machine designed to detect exactly one thing, and for more than 40 years, the people who have read that signal have not agreed on what it meant. The Vela satellites were designed to detect nuclear explosions from space. They were built by the United States Air Force, launched in pairs starting in 1963, and placed in high orbits more than 100,000 kilometers from Earth. Their primary instrument was the bang meter, an optical sensor named, in the curious way of Cold War engineering, after the Hindi word for cannabis, bang, because the scientists who developed it liked the sound. The bang meter was tuned to detect a very specific light signature, a double pulse, two flashes in quick succession. The first flash comes from the explosion itself, the fireball breaking through the surface of the atmosphere or the ground. The second comes a fraction of a second later, after the shock wave has made the fireball transparent and the interior of the blast becomes visible again. The interval between the two pulses, the shape of the light curve, is the signature of a nuclear weapon. No natural phenomenon produces exactly this pattern. On the 22nd of September, 1979, at 53 minutes past midnight Greenwich Mean Time, Vela satellite number 6911 detected that signature. The signal came from the southern Indian Ocean, approximately 2,500 kilometers south of South Africa, near the Prince Edward Islands. The double flash was unambiguous as a sensor reading. The satellite recorded it, encoded it, and transmitted it to ground stations. When analysts examined the data, they recognized immediately what the machine was telling them. Somewhere in the empty ocean between Africa and Antarctica, something had detonated with the light curve of a nuclear explosion. Almost from the moment the signal was received, the question was not whether the satellite had recorded what it recorded. It was who. The Partial Test Ban Treaty of 1963 prohibited nuclear weapon tests in the atmosphere, in outer space, and underwater. The Vela system existed to verify compliance. Every nuclear power on Earth knew the satellites were up there. Every nuclear power knew what they could detect. A test in the atmosphere in 1979 would have been, by any measure, a provocation, a violation of a treaty in force for 16 years, committed by a nation that believed it could escape detection, or that did not care if it was detected. The White House was notified within days. The Carter administration convened an expert panel, chaired by Jack Ruina, a professor of electrical engineering at the Massachusetts Institute of Technology. The panel included members from the Central Intelligence Agency, the Defense Advanced Research Projects Agency, and several academic institutions. They were given access to the raw satellite data, the calibration records, and the telemetry from the spacecraft itself. Their job was to determine, to the extent possible, whether a nuclear explosion had occurred. The Ruina panel's report, delivered in 1980, concluded that the signal was probably not a nuclear explosion, but it did not rule one out. The language was careful. The alternative explanation the panel considered most plausible was a micrometeoroid impact on the satellite, a small particle striking the spacecraft body and producing a glint of sunlight that entered the bang-meter aperture at just the right angle, with just the right timing, to mimic the double flash signature. This was not considered likely, it was considered possible. The panel judged it slightly more likely than a clandestine nuclear test, but it could not assign high confidence to either interpretation. The panel's conclusion, in other words, was a sentence that has hung over this event for more than 40 years. We do not know, but other data existed. The Ruina panel did not have sole access to the available evidence. The United States Naval Research Laboratory analyzed data from the Navy's hydroacoustic listening array, an array of underwater microphones on the ocean floor, originally built to track Soviet submarines. Those hydrophones had detected an acoustic signal from the region of the Prince Edward Islands at the time of the Vela event. The signal was consistent with a low-yield nuclear explosion. Not definitive hydroacoustic signals can be produced by other sources, but consistent and correlated in time and direction. The Arecibo Observatory in Puerto Rico, one of the most sensitive radio telescopes in the world, also detected something. An ionospheric disturbance, a ripple in the upper atmosphere traveling outward from the direction of the southern Indian Ocean. Nuclear explosions produce ionospheric disturbances. The signal matched what would be expected from a small atmospheric test. Neither of these additional data streams was sufficient to overturn the Ruina panel's conclusion on its own. But taken together, the optical double flash from the satellite designed to detect exactly that, the hydroacoustic signal from the ocean listening array, the ionospheric ripple from the radio telescope, the circumstantial case was stronger than the panel's language admitted. Some members of the panel privately believed that a test had occurred. Others were equally convinced that the satellite had malfunctioned. The group could not reach a consensus, and the published report reflected that division. One more piece of evidence surfaced later, and it came from an unlikely instrument: sheep. Australian researchers had, for years, routinely monitored the thyroid glands of slaughtered sheep as a way of tracking fallout from distant nuclear tests. Since iodine-131, a short-lived radioactive isotope produced by nuclear fission concentrates in the thyroid the way it would in a human exposed to the same fallout. A scientist named Lester Van Middlesworth, who ran one such monitoring program, found exactly that isotope in the thyroids of lambs slaughtered at a Melbourne abattoir in late October and early November of 1979, at levels consistent with recent exposure and decaying afterward at the correct half-life for iodine-131, not for anything else. Meteorologists later reconstructed the wind patterns for the days following the Vela detection and found that the prevailing westerlies sailors have long called this latitude band The Roaring Forties could plausibly have carried a fallout plume from the Prince Edward Islands across the Southern Ocean to southeastern Australia within days, arriving with rainfall that would have brought any airborne contamination down onto the same pastures where those sheep had been grazing. None of this proved a nuclear test had occurred. Iodine-131 can have other sources, and a wind pattern reconstruction is a model, not a measurement of the plume itself. But it was one more data stream pointing the same direction as the optical flash, the hydroacoustic signal, and the ionospheric ripple, and it was a data stream nobody had been looking for when they designed the Vela satellites in the first place. Decades later, in 2019, a further piece of the disagreement came to light. Documents declassified and published by the National Security Archive revealed that the Central Intelligence Agency, working independently of the Ruina panel, had assessed within months of the event that there was a probability of better than 90% that the flash had been a genuine nuclear test. Other officials within the Energy Department and the Defense Intelligence Agency reportedly held the same view. The Ruina panel's published conclusion, careful, hedged, ultimately inconclusive, was not, it turned out, a reflection of universal uncertainty inside the United States government. It was one institution's conclusion, reached at a moment when confirming a nuclear test by an ally would have created a diplomatic problem nobody in the Carter administration appeared eager to solve. The question of who might have conducted such a test took longer to develop. In the years after 1979, a body of evidence accumulated, much of it from investigative journalism and post-apartheid disclosures. Seymour Hersh, the American investigative journalist, published The Samson Option in 1991. The book argued that Israel had developed a nuclear weapons program with assistance from France, and that by 1979, Israel possessed operational nuclear weapons. The book further suggested that Israel had conducted a test in cooperation with the apartheid government of South Africa. South Africa, at the time, was under international arms embargoes and facing increasing isolation. It had its own nuclear weapons program, which was later acknowledged by the South African government after the end of apartheid. A 1997 white paper admitted that South Africa had produced 6 nuclear weapons, but did not confirm the 1979 test. The Israeli government has never confirmed or denied the Vela test. Its official policy on nuclear weapons remains one of deliberate ambiguity. Israel has never acknowledged possessing nuclear weapons. It has never signed the Treaty on the Non-Proliferation of Nuclear Weapons, and it has never explained what happened over the southern Indian Ocean in the early morning hours of the 22nd of September, 1979. What we know is this. A satellite built to detect nuclear explosions recorded a signal that looked exactly like one. A hydrophone network built to track submarines recorded a signal from the same location at the same time. A radio telescope recorded an atmospheric disturbance from the same direction. 2 nations, one in the Middle East, one at the southern tip of Africa, had the capability, the motive, and a documented history of defense cooperation, and the official panel convened to investigate the event produced a conclusion that did not confirm and did not deny, a document that left the door open to both interpretations. Because the alternative stating definitively that a United States ally had violated a treaty, the United States was obligated to enforce carried consequences the Carter administration may not have wanted to confront. This is the Vela incident. It is a mystery not because the evidence is absent, but because the evidence is ambiguous in ways that allow multiple interpretations to persist. The satellite did its job. It recorded what it was built to record. The uncertainty came afterward, in the rooms where the data was read. And the data is still there, in the archives, waiting for a definitive explanation that has not arrived. The satellite that recorded it was decommissioned long ago. Its successors are still in orbit, still watching. No comparable signal has ever been detected again, leaving the question of what, exactly, the Vela satellite saw, still open to the silence of the archive. What the Vela satellite saw was a flash of light produced by human action, a weapon test, or something that impersonated one well enough to fool a machine designed not to be fooled. The flash came from the Earth. It was made by us, or it was not made at all. There is another kind of flash. It does not come from the Earth. It comes from outside the solar system, from across the galaxy, and it arrives not on a satellite sensor but inside the human eye. During the Apollo missions to the Moon, astronauts reported seeing brief flashes of light even when their eyes were closed. In complete darkness, with the cabin lights dimmed and their visors covered, they saw streaks, points of light, and diffuse clouds passing through their visual field. The flashes lasted a fraction of a second. They came at irregular intervals, sometimes several in a minute, sometimes none for 10 minutes, and they occurred whether the astronaut was awake and attentive or drifting towards sleep. The first crew to report this was Apollo 11. Neil Armstrong, Buzz Aldrin, and Michael Collins noticed the flashes after they passed through the Van Allen radiation belts and entered deep space. They described what they were seeing to mission control. The reports were taken seriously, but the cause was not immediately obvious. The command module was a sealed pressure vessel. There was no light source inside the cabin that could produce what they described, and they were seeing the flashes with their eyes closed. A prediction had been made 17 years earlier. In 1952, Cornelius Tobias, a biophysicist at the Lawrence Berkeley National Laboratory, had conducted experiments using early particle accelerators to fire single-charged particles at samples of retinal tissue. He found that a single particle, passing through the retina, could stimulate the visual cells, directly producing a perceptible flash of light without any photon entering the eye. The mechanism was either Cherenkov radiation, the electromagnetic shock wave produced when a charged particle passes through a medium faster than light can travel through that medium, or direct ionization of the retinal cells themselves, triggering a nerve impulse indistinguishable from the one produced by real light. Tobias predicted that astronauts on missions beyond low Earth orbit, where the protective magnetic field of the Earth no longer shielded them, would experience this phenomenon. He had no way to test it. The cyclotrons at Berkeley could produce the particles, but they could not reproduce the sustained exposure of a deep space voyage. The predictions sat in the literature, unconfirmed, until Apollo. The particles responsible are called HCE particles, high atomic number and energy. They are the nuclei of heavy elements, iron and nickel and others, stripped of their electrons and accelerated to nearly the speed of light by supernovae and other violent astrophysical events. They cross interstellar space. They pass through the solar system. And when they encounter a spacecraft, they pass through that too. The aluminium hull of the Apollo command module was not a barrier to them. It was a thin film. The particles went through the metal, through the air inside, through the skin and skull and vitreous humor of the astronauts' eyes, and out the other side. What the astronauts saw was the fraction of those particles that happened to stimulate the retina on their way through. The rest passed silently, through the brain, through the optic nerve, through tissues that had no way to report what had touched them. On Apollo 15, 16, and 17, the phenomenon was studied systematically. An experiment called the Apollo Light Flash Moving Emulsion Detector was flown. It was a helmet-mounted device, worn by the astronauts for set periods, that used layers of photographic emulsion and plastic detectors to record the passage of cosmic ray particles. The principal investigator was Lawrence Pinsky at the University of Houston. The astronauts would report their flashes, and the detector would record the particle passages. The correlation was clear. When the astronauts saw a flash, a particle had passed through their head. The timing matched. The average frequency in deep space, outside the Earth's magnetosphere, was about one flash every 2 to 3 minutes. In the command module, the hull provided some shielding. On the lunar surface, where there was no spacecraft hull to slow the particles down, the rate was higher. During a sleep period, over 8 hours, an astronaut might experience 100 or more such flashes, each one a particle from outside the solar system, passing through the closed eye and into the brain. This is not a historical footnote. The same particle flux will be present on any mission to Mars. A round trip to Mars, with current propulsion technology, requires between 2 and 3 years in deep space, unprotected by Earth's magnetosphere or by the bulk shielding of a large space station. The particles that produce the flashes are the same particles that damage DNA, that break molecular bonds, that deposit energy in tissues, that repair slowly or not at all. The central nervous system is particularly vulnerable. The flashes of light are only the perceptible portion of a continuous bombardment, the part the retina can announce. The rest accumulates in silence. NASA and other space agencies have studied this problem for decades, and the honest answer is that we do not yet have a solution. The shielding required to stop HCE particles would be prohibitively heavy. A spacecraft built to protect its crew from this radiation would be too massive to launch. The alternative pharmaceutical countermeasures, biological interventions that accelerate DNA repair or protect neural tissue, is still experimental. The problem is recognized but unsolved, and until it is solved, every deep space mission beyond the moon will carry a crew that is, in a literal sense, being passed through by particles that originated in the deaths of stars. The most recent test of that problem did not happen in 1972. It happened this year. On the 1st of April, 2026, 4 astronauts aboard Artemis. 2 left low Earth orbit and traveled beyond the protection of the magnetosphere for the first time since the last Apollo crew did it more than 50 years earlier. Their spacecraft, Orion, carried a dedicated storm shelter, shielding built from materials that were already needed for other purposes, and sensors throughout the cabin recording the radiation environment in detail no Apollo mission had been able to capture. What those sensors confirmed was something engineers had suspected but never measured directly on a crewed flight: that shielding against galactic cosmic rays does not behave the way shielding against ordinary radiation does. A wall thick enough to stop an X-ray will simply absorb it. A wall struck by an HZE particle moving at a meaningful fraction of the speed of light can shatter that particle into a spray of secondary particles, including neutrons, that continue on into the cabin anyway in some configurations, more dangerous than if the wall had not been there at all. Radiation protection for this kind of particle is not only a question of mass, it is a question of geometry, of material choice, of timing flights to take advantage of the sun's own activity, since an active solar wind paradoxically pushes some galactic cosmic rays away from the inner solar system, even as it raises the risk of a flare. None of this solved the problem the Apollo crews first reported as flashes behind a closed eyelid. It confirmed, with modern instruments, that the problem is exactly as real and exactly as unresolved as the 1972 data suggested it would be now measured in a spacecraft carrying a living crew farther from Earth than anyone has traveled since. The Apollo astronauts did not express fear about this. The tone of the mission transcripts and the post-flight debriefings was observational. They reported what they saw. They asked if anyone else had seen it. When the mechanism was explained to them, they accepted it with the same pragmatic curiosity that characterized most of their responses to the unexpected conditions of spaceflight. The flashes were not painful. They did not seem to impair vision. They were simply there, a feature of the environment, like microgravity or the absence of atmosphere, to be noted and adapted to. But there is something about the image that stays with you. A person in a small metal room, far from any planet, eyes closed, and a light appears where there is no light. A particle that traveled across half the galaxy has crossed the boundary of the body and registered on the nervous system as a brief, silent streak. It did not ask permission. It did not notice the body was there. It passed through and continued, and the only evidence it left was a sensation that lasted less than a second. The particles are still arriving. They have been arriving for the entire history of the solar system, passing through the atmosphere, through the water, through every living thing on the surface. On Earth, the atmosphere and the magnetic field absorb or deflect most of them. Only a fraction reach the ground, and fewer still reach a human retina. In deep space, there is no such protection. The full flux is present, and the astronauts who have experienced it are, so far, the only human beings to know directly what it feels like to have the galaxy pass through them. And those particles are still arriving. What will they do to the astronauts who travel further to Mars and beyond? We do not yet know. There is a connection here to the earlier stories that is not metaphorical. The coronal mass ejection of 2012 passed through the point where Earth had been. The debris in orbit passes through the operational altitudes of active satellites. The mold on Mir passed through the titanium and quartz of the station's structure. The Vela signal passed through a satellite sensor and into the machinery of international secrecy, and the cosmic rays passed through the hull of a spacecraft and the closed eyelid of a sleeping astronaut. The universe, it turns out, is full of things that cross boundaries we think of as solid. The boundary between Earth and space, the boundary between the sealed room and the outside, the boundary between the body and everything else. These are gradients, not walls. And the stories we have been moving through tonight are all, in one way or another, about what happens when something on the other side of the gradient finds its way across. The cosmic ray flashes that Apollo astronauts experienced were produced by particles that had been accelerated by forces we can model but have never directly observed up close. A supernova explosion is one of those forces. When a massive star collapses at the end of its life, it ejects its outer layers at thousands of kilometers per second, and in the shockwave of that ejection, charged particles are accelerated to energies that can cross the galaxy. The particles that passed through the eyes of the Apollo astronauts were forged in explosions that occurred thousands or millions of years before the solar system existed. They had been traveling ever since, and one of those explosions was visible from Earth, in daylight, for 23 days. On the 4th of July, 1054, a star appeared where no star had been. It was visible in the daytime sky for 23 days. At night, it remained visible for 653 days, nearly 2 years before fading from sight. The astronomers of the Song dynasty recorded it. China at the time maintained an imperial astronomical bureau, a body of trained observers who tracked the sky for omens, for calendar keeping, and for the simple accumulation of knowledge about what happened above the empire. Their records were kept in the Song, the official history of the dynasty, compiled after its fall. The entry for the guest star is precise. It places the object southeast of the star Tianguan, which we now call Zeta Tauri, at the tip of the bull's horn in the constellation Taurus. It notes the duration. It notes the brightness. The record is dated. A guest star, in the terminology of Chinese astronomy, was any star that appeared where none had been before and then faded. Some guest stars were comets, which the astronomers distinguished by their motion and their tails. This one did not move. It brightened, held, and dimmed. It was a supernova. A separate record survives from Japan. The poet and courtier Fujiwara no Taika, writing in his journal The Megetsuki, noted the appearance of a guest star around the same date. His entry is briefer than the Chinese record, but it confirms the event from an independent source, at a different latitude, under a different sky. A third record comes from the Arab world. Ibn Butlan, a Christian physician working in Baghdad, recorded a star that appeared in the year 446 of the Islamic calendar and linked its appearance to a plague outbreak in the city. The connection was astrological in his telling the star as cause, the plague as effect, but the date and the description align with the Chinese and Japanese records. Europe, by every account we have, did not record the star. There is a single possible reference in the Cronaca Rampona, a manuscript from northern Italy, but it is ambiguous in dating and description. The absence is not fully explained. The star was bright enough to be seen in daylight for 3 weeks. It was visible at night for nearly 2 years. It was the brightest stellar event in recorded human history, and yet no European chronicle, no monastery annal, no letter or diary from the continent that would later give birth to modern astronomy mentions it. The reasons are a matter of speculation, cloudy skies, political upheaval, the fragmentation of learning after the fall of the Western Roman Empire, or simply that someone saw it and wrote nothing down. The silence is one of the small mysteries that surrounds this event, the kind that historians argue about in journals and never fully resolve. The supernova of 1054 left a remnant. 6 centuries later, in 1731, an English physician and amateur astronomer named John Bevis was surveying the sky with his telescope when he came across a patch of nebulosity in Taurus. He noted its position and appearance. In 1758, the French comet hunter Charles Messier was searching for the predicted return of Halley's comet when he encountered the same nebula. He initially mistook it for the comet, then realized it was stationary, a permanent cloud, not a visitor. He catalogued it as Messier 1, the first entry in his famous list of objects that are not comets, a list he compiled so that other comet hunters would not waste their time on these immovable smudges of light. The Crab Nebula, as it came to be called after a drawing by Lord Rosser in the 1840s that showed filamentary structure resembling the legs of a crab, is the expanding debris of the 1054 supernova. In 1913, Vesto Slipher at the Lowell Observatory in Arizona pointed a spectrograph at the nebula and measured its motion. The spectral lines were shifted. The cloud was expanding. Slipher's measurement allowed astronomers to work backward and estimate when the expansion began. The answer pointed toward the 11th century. In 1928, Edwin Hubble, the same Hubble whose name is now on the Space Telescope, published the definitive connection. He compared the Chinese records of the guest star of 1054 with the measured expansion rate of the Crab Nebula, the position of the nebula relative to Zeta Tauri, and the optical appearance of the cloud. The fit was exact. The guest star of 1054 was the explosion that created the crab. For the first time, a historical astronomical record from the pre-telescopic era had been linked unambiguously to a specific astrophysical object. At the center of the Crab Nebula is the Crab pulsar. It was discovered in 1968 by Jocelyn Bell Burnell, then a graduate student at the University of Cambridge, working under the supervision of Anthony Hewish. The instrument was a radio telescope. She had helped build a field of wooden posts and wire, covering more than 4 acres, designed to detect the scintillation of distant radio sources. In the data from that telescope, Bell Burnell noticed a signal that did not look like scintillation. It was a regular pulse, repeating every 1.33 seconds, too fast and too precise to be anything terrestrial. The discovery of the first pulsars Bell Burnell found a second one within weeks was one of the major astronomical events of the 20th century. The objects were soon identified as neutron stars, the collapsed cores of massive stars that had exploded as supernovae. A neutron star packs roughly 1.5 times the mass of the Sun into a sphere about 10 kilometers across. It is so dense that a teaspoon of its material would weigh billions of tons on Earth, and it spins. The Crab pulsar rotates 30.2 times per second. Its magnetic field, focused into beams of radiation that sweep across the sky like a lighthouse, is so powerful that it accelerates particles to energies that produce the glow of the surrounding nebula. The Crab pulsar alone radiates 75,000 times the total luminosity of the Sunday. It powers the entire nebula from a sphere smaller than the city the listener is in right now. Anthony Hewish received the Nobel Prize in Physics in 1974 for the discovery of pulsars. Jocelyn Bell Burnell was not included. The omission became one of the most discussed decisions in the history of the prize. Bell Burnell herself has consistently declined to express bitterness about it, stating that she was a graduate student at the time and that the convention of the era was to award the prize to the senior researcher. Others have been less restrained on her behalf. The pulsar discovery, in any case, was hers. She noticed the signal. She pursued it. She convinced Hewish that it was not interference, and her name is permanently attached to the moment when humanity first detected the spinning remnant of a dead star. The Crab pulsar is still spinning. The nebula is still expanding at roughly 1,500 kilometers per second. The particles it accelerates are still crossing the galaxy. Some of them will eventually reach the solar system. The connection between the supernova of 1054 and the cosmic ray flashes the Apollo astronauts saw is direct. Heavy nuclei, iron, nickel, and heavier elements are forged in the interiors of massive stars and dispersed by their explosions. The shock wave of a supernova is one of the few mechanisms in the universe capable of accelerating these nuclei to the relativistic energies that make them HZE particles. The Crab Nebula is not the only source of such particles, but it is one of the closest and most energetic. The star that exploded in 1054 is still, 970 years later, sending fragments of itself across the galaxy at nearly the speed of light. What the Song Dynasty astronomers saw was the light of the explosion itself, the electromagnetic radiation that traveled roughly 6,500 light-years from the nebula to their eyes. What the Apollo astronauts felt was the matter of the explosion, the actual nuclei of atoms that had been inside the star before it died, arriving decades or centuries after the light, because they travel slightly slower than light, and because they are deflected by magnetic fields along the way. The light and the matter are the same event, arriving at different times, through different channels, registering on different instruments. The naked eye of an imperial astronomer in Kaifeng in 1054, and the closed eye of an astronaut in a command module in 1969. The Songshi is a bureaucratic document. It was compiled by scholars working from the records kept by the astronomers themselves, and its tone is administrative. It does not describe the emotional response of the observers. It records position, duration, and brightness. But the act of recording it at all, with sufficient precision to identify the remnant 9 centuries later, is a kind of relationship with the sky that we have inherited. The astronomers who wrote those entries did not know what a supernova was. They did not know about neutron stars or pulsars or HZE particles. They knew that something had appeared where nothing had been, and they wrote it down. And their writing became part of the chain of evidence that led to the Crab pulsar, to Jocelyn Bell Burnell's chart recorder, to the understanding that the atoms of dead stars pass through the bodies of living people. The supernova of 1054 is an example of a historical record confirmed by physical evidence. The guest star was seen, the remnant is there, the link is secure. But not every historical record of a celestial event has been confirmed. Some remain suspended between the written word and the physical world, neither validated nor dismissed, waiting. On the evening of the 18th of June, 1178, 5 monks of Christ Church Cathedral Priory in Canterbury, England, were standing outside after sunset. The moon was a thin crescent in the western sky. The monks reported to the chronicler Gervase that they saw the upper horn of the crescent moon split in two, and from the split a flaming torch emerged, and the moon itself writhed like a wounded snake. Gervase of Canterbury recorded their account in his chronicle. The monks swore to its truth. They were, by Gervase's account, reputable men. The description is vivid. The upper horn of the crescent moon split the bright limb of the satellite, seen edge-on, breaking apart. A flame emerged from the break. The moon appeared to move, to writhe. The event lasted long enough for the monks to observe it, describe it, and report it. Then it was over. In 1976, a geologist named Jack Hartung published a hypothesis. He proposed that the monks had witnessed the formation of a specific crater on the moon, Giordano Bruno, a 22-kilometer-wide impact structure on the lunar far side, located at 35.9 degrees north, 102.8 degrees east. Giordano Bruno is one of the youngest large craters on the moon. Its ray system, the bright streaks of ejected material that radiate from a fresh impact, is still visible. In lunar terms, it is pristine. Hartung calculated that a 1 to 3 kilometer asteroid striking the moon at solar system velocities would produce a plume of vaporized rock, rising thousands of kilometers above the surface, briefly visible from Earth, as a torch of flame emerging from the limb. The impact would be large enough to create a crater of roughly 22 kilometers. The plume would be visible for several minutes. The timing, the description, and the physical characteristics of the crater seem to align. If Hartung was right, the Canterbury monks are the only human beings in recorded history to have witnessed the formation of a lunar crater. The crater they saw created is there. We have photographed it from orbit. But the hypothesis has a problem, a large one. In 2001, Paul Withers and a team at the University of Arizona calculated the consequences of such an impact. An asteroid large enough to produce a 22-kilometer crater on the moon would also produce a substantial amount of debris that would fall to Earth. Within a week of the impact, they estimated, Earth would have experienced a meteor storm of extraordinary intensity on the order of 10 million meteors per hour. The sky would have been filled with shooting stars. The storm would have been visible from every inhabited continent. It would have been terrifying, or beautiful, or both. And it would certainly have been recorded by someone, somewhere, in the thousands of chronicles, annals, and letters that survive from the 12th century. No such record exists, not one. From Europe, from China, from the Islamic world, from India, from any culture that kept written records in the late 12th century, there is no mention of a meteor storm in June of 1178. The silence is comprehensive. Imagine the visual spectacle of such a storm. 10 million meteors per hour means roughly 3,000 meteors streaking across the sky every second. The night would have been brighter than a full moon, with trails of light crisscrossing from horizon to horizon, a continuous cascade of fire. It would have been visible globally, for hours, perhaps days. The fact that no chronicler, no poet, no scribe anywhere on Earth mentioned such an event is powerful evidence that it did not happen. A second line of evidence came from the Japanese lunar orbiter Kaguya, which arrived at the moon in 2007. High-resolution imaging of Giordano Bruno crater allowed scientists to count the number of smaller craters that had formed on its floor and ejecta blanket since the original impact. The density of those craters is a clock. The longer a surface has been exposed, the more impacts it accumulates. The Kaguya data suggested that Giordano Bruno is between 1 and 10 million years old. Even the lower bound of that range is 1,000 times older than the monk's report. The crater was there, ancient and undisturbed, long before the Canterbury Priory was built. The scientific case for the 1178 impact, in other words, has largely collapsed. The meteor storm that should have occurred did not. The crater that should be 800 years old is millions of years old. The alignment of description and physical feature that Hartung proposed was probably a coincidence. What, then, did the monks see? The most likely explanation is that they witnessed a meteor entering the Earth's atmosphere, aligned by chance with their line of sight to the moon. A bright fireball, breaking up as it descended, could produce a flame-like appearance and a visible distortion of the background sky. If the meteor passed directly in front of the crescent moon from the monk's vantage point, the flame would have appeared to emerge from the moon itself. The writhing could have been an atmospheric effect, the turbulence of the fireball's wake distorting the image of the lunar crescent behind it. The monks, looking up at the right moment, would have had no way to distinguish a meteor in front of the moon from an event on the moon itself. They lacked the concept of a meteor as a physical object entering the atmosphere. They described what they saw in the language available to them. The alternative explanations include an atmospheric optical phenomenon, a parhelion, a circumhorizontal arc, some trick of ice crystals in the upper air catching the last light of sunset, or a volcanic emission from somewhere on Earth, or a transient lunar phenomenon of the kind that modern amateur astronomers occasionally report and that professional astronomers mostly dismiss. None of these explanations is fully satisfying. None of them produces the specific image of a flaming torch emerging from a split in the moon. The monk's report remains what it has always been, a written account, sworn to by 5 witnesses, recorded by a reputable chronicler that describes something extraordinary and resists satisfactory explanation. It is not proof of a lunar impact. It is not proof of anything. It is a piece of data that does not fit. The monks of Canterbury are not famous. Their names were not recorded. Gervase, the chronicler, is a minor figure in medieval English history, known mostly to specialists. The event they witnessed is a footnote in the literature of historical astronomy, a curiosity that was briefly famous in the 1970s and has since receded. But the image they left behind, 5 men in the grounds of a priory, looking up at a crescent moon and seeing something that should not have been there, is the kind of image that settles into the silence of a dark room and stays. And it raises a question: what has been seen that was never recorded, and what has been recorded that we have not yet learned to read? Most of the events we have been moving through tonight are events for which physical evidence exists. The coronal mass ejection of 2012 was recorded by a spacecraft. The debris in orbit is tracked by radar. The reactor from Cosmos 954 was recovered from the Canadian tundra. The mold on Mir was cultured and photographed. The Vela signal exists in the archives. The Apollo astronauts filled out debriefing forms about the flashes they saw. The Crab Nebula is visible through a small telescope. Even when the interpretation is ambiguous, the data is real. The monk's report is different. The data is only words. The physical evidence, if there ever was any, has not been identified. And yet the report persists, because it was written down by someone who believed it, and because it raises a question that the confirmed events also raise, in a quieter way. The supernova of 1054 was recorded by 3 cultures and missed by a 4th. The event over the Indian Ocean in 1979 was recorded by a satellite, a hydrophone array, and a radio telescope, and the interpretation is still contested. The flashes in the eyes of the Apollo astronauts were predicted before they happened and confirmed when they did, and the astronauts are the only human beings who have experienced them directly. The universe is full of signals. Some of them are unmistakable. Some of them are ambiguous. Some of them are probably mistakes. And then there is a category of signal that is not ambiguous at all, a clear detection, a long-duration event, recorded by multiple instruments, that simply refuses to fit the categories we have built for it. One of those arrived on the 14th of June, 2006. On the 14th of June, 2006, a satellite called Swift was looking at the sky. Swift had been launched 2 years earlier by NASA, with international partners, to detect gamma-ray bursts, the most energetic explosions in the universe, brief flashes of gamma radiation that outshine entire galaxies for a few seconds before fading. The satellite's design was straightforward. It carried a gamma-ray detector that could identify a burst and, within seconds, swivel the spacecraft to point X-ray and ultraviolet telescopes at the source. The goal was to catch the afterglow of the burst before it faded, to pin down its location precisely, and to alert ground-based telescopes so they could study what remained. At 0612 Universal Time, SWIFT detected a burst. It was designated 060614, the date, in the format of astronomers. The burst lasted 102 seconds. 102 seconds is a long gamma-ray burst. In the classification system that astronomers had built over the previous decade and a half, gamma-ray bursts came in two types. Short bursts, lasting less than 2 seconds, were understood to come from the merger of two neutron stars, or a neutron star and a black hole compact objects spiraling together and colliding in a final cataclysm. Long bursts, lasting more than 2 seconds, came from the collapse of massive stars, the same kind of supernova that had produced the Crab Nebula. The distinction was physical: different progenitors, different mechanisms, different afterglows. A 102-second burst was, by this classification, a long burst. It should have come from a collapsing massive star, and a collapsing massive star should leave behind a supernova, a brightening point of light, visible for weeks or months, at the location of the burst. SWIFT's rapid alert system worked as designed. Within minutes of the detection, the spacecraft had determined the position of the burst and transmitted it to the ground. Within hours, telescopes around the world were slewing toward a point on the sky in the constellation Indus. The location was precise. A faint galaxy was visible at that spot, roughly 1.6 billion light-years from Earth. A dwarf galaxy, small and relatively dim, of a type common in the universe. And then the astronomers waited. A supernova from a collapsing star takes a few days to reach peak brightness after the gamma-ray burst. The telescopes watched the location night after night. The Hubble Space Telescope was brought to bear. The Very Large Telescope in Chile, the Keck telescopes in Hawaii, the Gemini telescopes in both hemispheres, all of them watched the same patch of sky, waiting for the light of the supernova to rise. At the California Institute of Technology, Avishai Galyam and his team checked the data each morning. At NASA's Goddard Space Flight Center, the SWIFT principal investigator Neil Gehrels monitored the observations. They were looking for the telltale rise of a supernova spectrum, the characteristic lines of oxygen and silicon expanding outward at thousands of kilometers per second. They saw nothing. The sky remained dark at the location of the burst. The upper limits on any supernova brightness grew tighter with each passing night. The Hubble observations went deep enough to detect a supernova 20 times fainter than any previously known. Still nothing. The galaxy at the burst location showed no brightening at all. The afterglow of the burst itself faded on schedule, declining through the X-rays and the optical and the radio, and when it was gone, only the faint dwarf galaxy remained, unchanged. This was not supposed to happen. A long gamma-ray burst without a supernova was, in the framework of the time, not a category of event. The framework had to be wrong, or the event had to be something new. The team led by Galyam and Gehrels published their analysis in Nature in December 2006. They proposed a solution. The burst, designated 060614, they argued, was a new kind of event, a hybrid gamma-ray burst. It had the duration of a long burst but no associated supernova. Its host galaxy was a dwarf with very few massive stars, the wrong environment for a collapser. The burst did not fit in either box. The boxes needed to be redrawn. The competing interpretation came from Bing Zhang at the University of Nevada, among others. Zhang proposed that the burst might have been a short burst, a neutron-star merger that somehow produced an extended emission tail lasting 100 seconds. The merger itself would be over in less than 2 seconds, but the interaction of the merger remnant with surrounding material could, in principle, produce a longer gamma-ray signal. The problem with this interpretation was that no other short burst had ever produced an extended tail of this duration and character. It would require a special set of circumstances, a fine-tuned scenario that matched this one event but had no other examples. A second hybrid burst was found in 2008, designated 080503. It had the same signature: long duration, no supernova, a host galaxy with few massive stars. Two events do not make a large sample, but they make it much harder to dismiss the first one as an instrument error or a statistical fluke. The hybrid category was real. Something in the universe was producing long gamma-ray bursts without the deaths of massive stars. What that something is remains unknown. The leading hypotheses include the tidal disruption of a white dwarf by a black hole, a smaller, denser star being torn apart by a more massive companion, or a new type of supernova that produces a gamma-ray burst, but for reasons of mass or metallicity or some other factor, fails to produce a bright optical afterglow. Neither hypothesis has been confirmed. The data does not exist to distinguish between them. The hybrid bursts remain what they were in 2006. A signal we received, a signal we measured precisely, and a signal that tells us our categories are incomplete. The dwarf galaxy that hosted the burst of 060614 is still there, in Indus, faint and small. It has given no indication that anything else unusual has occurred within it. The burst came and went. The light of it crossed 1.6 billion light-years to reach Swift's detector, and most of that light has now passed the Earth and is receding into the space beyond. The event is over. What produced it is still happening somewhere in the universe. Other hybrid bursts have been detected, a small but growing population, but the specific burst of the 14th of June, 2006, is now part of the archive, waiting for a theory that can hold it. What do we do with a signal that refuses to be classified? We hold it, we publish it, we argue about it in the journals and at conferences. We wait for more data, more examples, a pattern that reveals itself only after the third, or the fifth, or the 10th event. And in the meantime, we acknowledge that the signal exists, that it was recorded, that it means something even if we do not yet know what. Some of that data has already arrived. On the 11th of December, 2021, 15 years after the burst from Indus, a different satellite recorded a different long gamma-ray burst, lasting about 50 seconds, coming from a spiral galaxy roughly 1 billion light-years away in the constellation Boötes. A team led by researchers at Northwestern University did what every team before them had done with a long burst. They began watching for the rising light curve of a supernova. Instead, over the following days, they found something with a completely different signature, a faint, fast-fading, distinctly red glow, fading on a timescale and in colors that did not match a supernova at all. It matched a kilonova, the specific glow produced when two neutron stars, or a neutron star and a black hole, spiral into each other and merge, flinging out a wash of heavy, freshly synthesized elements that light up briefly as they decay. A kilonova had been seen once before, in 2017, paired for the first time with both a gravitational wave detection and a short gamma-ray burst, the kind every model agreed a merger should produce. It had never been paired with a burst this long. Deep imaging from the Hubble Space Telescope, taken weeks later, ruled out a supernova at the location to an extraordinary depth, with nothing found. The kilonova was real, and so was the long burst. And for the first time, the two were confirmed to come from the same event. This does not resolve what produced the burst from Indus in 2006. That galaxy was different, small, faint, sparse in massive stars, and its burst has never shown the telltale red glow of a kilonova in the data that exists for it. But it changes what we now know is possible. A burst lasting 50 seconds or more, the duration that for decades was treated as a near-certain signature of a dying massive star, can also come from two compact objects colliding into one. The category that seemed settled a generation ago, long burst, means collapsing star. Short burst means merger has had to be redrawn twice now, once by a burst with no supernova at all, and once by a burst with a merger's own fingerprint sitting in plain sight where no one had thought to expect it. The final parallel is not to the Vela signal or to the monks of Canterbury, but to the first story we sat with tonight. The coronal mass ejection of 2012 was recorded by a spacecraft placed in its path. The measurements were clear. The implications were clear. The event missed the Earth by 9 days. It was not ambiguous. It was not unclassified. It was a solar storm of Carrington magnitude, passing through empty space, and the only question it left open was when the next one would be aimed at us. Some of the events in this video are mysteries because we lack the evidence to resolve them. Some are mysteries because the evidence is there and we have not yet learned to read it. And some are not mysteries at all. They are warnings. The dark room you are in right now is not empty. It is crossed, constantly, by particles that were produced by events like the ones we have described. Cosmic rays from the Crab Nebula and a million other supernovae. Solar wind particles from the Sun's corona, some of them from the same active regions that produced the 2012 coronal mass ejection. Neutrinos from the core of the Sun, passing through the Earth as if it were not there. And dark matter particles, whatever they are, whatever they turn out to be, passing through in numbers that dwarf everything else. The boundary of the body is not a boundary to these things. The skin, the closed eye, the skull, these are permeable membranes. The particles pass through. Most of them leave no trace. Some of them, the HZE nuclei, trigger a flash of light in the retina that you would see if you were in deep space, away from the Earth's magnetic field. A few of them deposit enough energy to break a DNA strand, and the cell repairs it, or does not, and the repair succeeds, or fails, and the failure accumulates, or is cleared, or is not. The process is statistical. It has been happening for the entire history of life on Earth. It will continue. The difference, tonight, is only that you know it is happening. The particles are not metaphors, they are physics. They are the messengers of events that occurred before the solar system existed, or events that occurred last week on the surface of the Sun, or events that are occurring now, at this moment, in galaxies too distant for their light to have reached us. The universe is not a distant spectacle. It is a medium. We are immersed in it. It passes through us. The strongest fact we have sat with tonight is this. On the 23rd of July, 2012, the Sun produced a coronal mass ejection with enough energy to collapse modern civilization. It crossed the orbit of Earth at the exact location our planet had occupied 9 days before. A spacecraft called Stereo A measured it. The magnetic field reading came back at 80 nanotesla. The economic damage, had it struck, would have been measured in trillions of dollars, and the recovery would have been measured in years. We missed it by just over a week, and the Sun will produce another. We do not know when. The Sun does not operate on a schedule we can predict with precision. The Carrington event was 1859. The next Carrington-class coronal mass ejection that we detected in situ was 2012, a gap of 153 years. But the statistics are sparse. The events we have measured are few. The next one could be a century away, or it could be in progress now. The plasma already crossing the distance between the Sun and the orbit of Earth, the magnetic field lines already curling into the configuration that will couple with our magnetosphere and drive currents into the ground beneath us. We have placed more in orbit since 2012, more satellites, more debris. The Kessler cascade threshold is closer. The grids on the ground are more interconnected, which makes them more vulnerable to a geomagnetic disturbance. A failure in one region cascades into others because the power has to go somewhere, and if the transformers in one state or province go down, the load shifts to the neighbors, and they go down too. We have not hardened the grid against a Carrington-class event. The transformers that would need to be replaced are still custom-built, still weighing hundreds of tons, still requiring a year or more to manufacture. The stockpile is small. This is not a prediction of catastrophe. It is a statement of probability. The event will happen. We do not know when. We know it will happen because it has happened repeatedly in the past that we can measure, and the Sun's physics has not changed. The question is whether we will be ready, and the honest answer is that we are not, and we know we are not, and we have not done what we know how to do. The 2012 coronal mass ejection missed. It passed through the dark. The only reason we know about it is that we put a spacecraft in its path, and that spacecraft told us what had crossed. The listening continues. Stereo A is still out there, still watching the Sun from its orbit ahead of the Earth. Other spacecraft watch too. The Solar and Heliospheric Observatory, the Parker Solar Probe, the Solar Orbiter, a fleet of instruments pointed at the star we depend on, measuring its magnetic field, its particle output, its flares, and its coronal mass ejections, sending data back to the ground every day. We have built an early warning system of a kind. It gives us hours, sometimes a day or two, to prepare for an eruption after we see it launch. That is enough time to shut down vulnerable transformers, to put satellites into safe mode, to warn the power grid operators. It is not enough time to replace the transformers. It is not enough time to build a stockpile. It is enough time to minimize damage, if the warning is heeded, if the protocols are followed. The next Carrington-class coronal mass ejection will be the first one to arrive in a world that has advance warning of its approach. The test will be whether we use the hours we are given. In the quiet of this room, as the video reaches its end, the image to hold is not the storm itself, it is the gap. 9 days, a small number, measured against the 4.5 billion year history of the planet, or the 150,000 year history of our species, or the 153 years since Carrington saw the white light on the Sunday 9 days. The time it takes for the Earth to move a little further along its orbit, a little further from the place where the plasma crossed. If the Sun had erupted 9 days later, everything we have talked about tonight, the debris in orbit, the reactors, the mold, the rock that skipped back into space, the false alarm in a Soviet bunker, the signals, the flashes, the supernovae would have been framed by a different set of events on the ground. A global blackout, a multi-year recovery, a reminder, visible to everyone, that the star we circle is not constant. We are protected by distance and by probability and by the thin magnetic field of the Earth. And those protections are real, and they work, and they are not complete. The gap between a near miss and a direct hit is the difference between a story we tell after the fact and a story we live through. Tonight, we have told the first kind of story. The second kind will happen. It is only a matter of time. Not every near miss in this video arrived from outside the atmosphere. The closest this planet came to catastrophe tonight did not begin with a flare or a flash. It began with sunlight glancing off a layer of cloud at the wrong angle on the wrong night of the year, read by a satellite that had no way to distinguish a reflection from a rocket engine. 25 minutes is roughly how long the warning had to be doubted before the silence on the ground confirmed what one officer in a windowless room had already decided to believe. The distance between that night in 1983 and a war that would have killed more people than every other event in this video combined, several times over, was the judgment of a single person who understood his own instrument well enough to know when it was lying to him. And not every signal in this video came from something we could eventually explain. A storm can be modeled, a reactor's failure can be traced to a stuck valve and a budget that should have paid for a backup. But a radio telescope in a field in Ohio recorded 72 seconds of something, once, in 1977, at a frequency chosen with apparent care, shaped exactly the way a real signal, from a real point in the sky, should be shaped, and then never again, not that night, not in the decades of listening since. We have a record of it. We do not have an explanation for it. Both of those statements remain true at the same time, and neither one is going away. And now, as you lie here in the dark, the particles are still passing through. Some of them are from the sun, the quiet solar wind, the steady outflow of protons and electrons that the magnetosphere deflects toward the poles, where it produces aurora that someone, somewhere, is watching. Some of them are from the Crab Nebula, the remnant of the star that appeared in 1054 and stayed visible for 2 years. Some of them are from the hybrid gamma-ray burst of 2006, though their numbers are too small to measure, and their energy is too low by the time they cross 1 billion light-years. Somewhere above this room, on a path nobody is currently tracking, a small fragment of rock that skimmed across 3 states and 2 Canadian provinces in 1972 is still in its orbit around the Sun, having passed close to this planet once already and not yet announced when or whether it will again. Some of them are from sources we have not identified, events we did not record, explosions that occurred before the Earth existed and whose messengers are arriving now, in this room, through your body, silent and invisible and innumerable. The universe is not a place we observe from the outside. It is a thing we are inside. It crosses the boundary we think of as the self, constantly, without friction, without announcement. We know some of what passes through. Most of it we do not know. The fact that we know some of it, that we can name the Crab Nebula, that we can measure the 2012 coronal mass ejection, that we can record a gamma-ray burst and argue about what it means is itself remarkable. We are a species that learned to detect things that are invisible, to measure events that occurred before we existed, to build machines that watch the sun and listen to the ocean floor and catch flashes of light from the edge of the observable universe. And, on one occasion, to recognize that a reflection in a cloud was not a missile, before it was too late for the recognition to matter. We have done this, and we have done it, for the most part, not out of fear but out of the desire to know what is there. The knowing is not complete. It will never be complete. There will always be another signal that does not fit the categories, another near miss we only recognize in retrospect, another organism growing in the sealed room we thought we had sterilized. The incompleteness is not a failure. It is the condition of looking. The universe is larger than our ability to model it, and it always will be, and that is not a problem to solve. It is the reason the sky is worth watching. Good night.